All right, in this video, I'm going to give you sort of a brief explanation of how to start thinking about this situation. It's a version of something called an Atwood machine, and we'll talk about that more in class. But I just wanted to give you guys this to give you maybe a little jump start on the quote-unquote homework I gave you to think about this situation. So we've got mass 2 hanging, okay, from a string over here. Make sure I'm drawing. Okay, mass 2 hanging from a string over here, and mass 1 is what I called the cart, the car. I apologize if you can hear my dog whining. He's fine. He's just bored. So mass 1 is what I've called the car on the track. Okay, again, we're ignoring any friction that might be present, okay, in order to give ourselves an ideal situation. So there's a couple of ways we can think about this. We can think about it as having two distinct things happening. One, the mass 2 falling, and 2, mass 1 moving down the track. So if we do that, okay, for the car, okay, our free body diagram looks something like this. We've got, of course, gravity acting on my cart. Okay. We've got the normal force acting on my cart. Okay, so label those M1G and normal force. Okay, and actually, in this case, it doesn't take a lot to convince yourself that the normal force is going to be equal in magnitude to the force of gravity on this. So those are actually going to end up canceling out. The reason for that is we know the car is not going to be accelerating in the vertical direction at all. It's only going to move horizontally with some acceleration down the track. Okay, as mass 2 will move down with some acceleration. Okay. And then, of course, lastly, we have to include the tension, okay, from the string. Okay. Right. So 3 forces. Okay. Really one force that's unknown. Okay. And if we look at the hanging mass, okay, if we consider the hanging mass, its free body diagram, okay, only has 2 forces actually. Has gravity, m2 times g, it has the tension, pulling up. Okay. Now, in this case, okay, unlike with the car, okay, we do have acceleration in the vertical direction. This is going to fall. Okay? There's no two ways about it. It's going to fall, which means in comparing the tension force with the force of gravity down here, okay, we know gravity must be winning. Okay, so gravity has to be greater, but we don't know much more than that about the tension force. What we can conclude, however, is okay, the tension pulling on mass 2 here, okay, and the tension pulling on mass 1 here, okay, they're in the same string, okay, and it's one of the rules of tension in strings and ropes and cables that the tension anywhere in the string has to be the same. You can't have varying tension within one rope, okay? However hard you pull on one side, okay, the other side is going to pull just as hard. Okay, so in fact, these two tension forces will be exactly the same in magnitude, even though they're in different directions. That's what this pulley does. Okay, pulley is a simple machine that changes the direction of an applied force. Okay. So feels like a pretty complicated, situation. We've got 2 different free body diagrams, 2 different masses, 2 different sort of things going on, 2 different events happening. Okay, but consider, since these 2 are fixed to one another, since the distance between them is a fixed value, okay, this acceleration it's exactly the same as the acceleration of the car. In other words, as mass 2 falls at some rate, okay, that got messy. Okay, as mass 2 falls at some rate, okay, the car is going to accelerate to the right at the exact same rate. Okay, they can't possibly be moving at different speeds, otherwise the string would break. Okay, so if we consider, okay, so I just switched pages here. All right, if we consider instead that they are just one system, okay, and by that I mean we consider mass 1 and mass 2 to be essentially one object that has one total mass, that has some net force applied to it, okay, and then accelerates at some rate. Okay, so the mass of our total system, okay, would be mass 1 plus mass 2. Okay, don't know the acceleration. What we do know, however, is that the only external force that's causing acceleration, okay, external force means coming from outside of the system. Our system includes mass 1, mass 2, mass 1, and the string, okay? String is inside the system. Okay, the string is part of the system. Okay, now we're assuming it has no mass, okay, which is a decent approximation. Strings are usually very light, particularly compared to a car and a hanging mass. Okay, we're considering that to be inside the system. So any forces that it generates, we don't take into account. Tension is not taken into account here. It's not an external force. Okay, the only external forces are gravity, and then of course the normal force that's being applied over here. But as we looked at in the first part, okay, this normal force is canceled out by the gravity pulling down on cart 1, or excuse mass 1. Okay, so that is not going to affect anything. The only thing that's having an unbalanced force act on it, unbalanced external force, is this mass. Okay, and of course we know what that force is. It's m2 times g. Okay, so the force applied to the system, okay, or I should say the net force, okay, the net force applied to the system is only m2g. That's the only force that's coming from outside of the system that's not being balanced. Okay, the tension is here, but the tension is inside the system. Okay, so we're not taking that into account. Okay, this idea of a closed system that includes some of these things is a complicated idea, but it can really simplify things for us. Okay, so this is the force applied. Okay, if we apply a certain amount of force, okay, to some mass, we can figure out exactly how it's going to accelerate. So I'll leave it there, and knowing that we know the net force, we know the mass of the system, okay, we'll look at a little further sort of the implications of this and the answers that come out of it in class next time.